Hello everyone, this is Mark. Welcome to my multivariable calculus video. Today we're going to talk about vector value functions. And the first question I have here for today is, what is the most important thing in vector calculus? This is an open-ended and then more of an opinionated question, but for me, after helping students work Calc 3 over 2 years, I think the most important thing in vector calculus is parameterization, okay? Parameterize. You need to parameterize your vector value functions before you can solve any of the problems related to them, okay? And this is this quote, this exact quote, will come back to you later down in Calc 3, particularly in chapter 17. But that's a couple of months away for you for now. But I do want to bring this up early so that you are aware of this thing, so that you don't get confused when you at the beginning of the problem. Okay, so this is a technical question. How can you tell the orientation of a curve, right? For a function that's describing a circular motion, for example, how can you know which direction is the particle traveling, right? I know for many people, I'm sure they have like their own unique way, or maybe even fancier way, to tell the parameter orientation of a curve. But for me, I like to brute force through this type of problems. Is I'm just gonna plug points in. Right? I find a few points, I plug them in, and I map them out on my 3D coordinates, or 2D coordinates for the matter, and then I can see where the particle is traveling, right? Hence the orientation of the curve. How can you find the intersection between the curve and a 2D surface, right? I'm in my previous videos, I have talked about the concept of finding the intersection between a line and a plane, right? A curve is just a fancier version of a line, right? It's still a one-dimensional object in 3D, and the 2D surface is also just a fancy version of a plane, right? It's a 2D object in the 3D space. So remember the sort of a mnemonic technique that I have taught you before, right? Is plug in the line into the plane. I'm gonna shrink this down a little bit. Right, plug in the line into the plane. Right. So if we expand that idea a little bit, right, it's the same. It's plug in the curve into the surface. Right. The concept is the same, but we are just leveling up the idea from line to curve and from plane to surface. I hope that makes sense a little bit to you. And then we will apply this idea into some practice exam problems. Okay, and then here's the first one for you. And I'm gonna go ahead and switch to a few notes that I have prepared. 14.1 pager and then one right here. So I am going to switch orientation. Perfect. Okay. Oh, actually, let me go back. I just want you to read this question. I don't mind about showing the answer to you at all, actually, to be honest with you. You know what? Maybe not. I'll show you the answer this time. Maybe next time I'll hide it for you. But this is not the main point for now. But right now I want you to identify the type of question, right? I want you to identify the type of question and then have an idea of what we are looking at. So what is the x-coordinate of the point which the curve defined by this intersects with a cone? It's this for t greater than 0. So I think this is an intersection between a line, or between a curve between a curve and a surface, right? It's a quadric surface to be exact, but it doesn't have to be, right? So this is the idea, right? So as we have said here, right, it's the problem type is the intersection point between a curve and a surface, and the keywords is that we have a curve that's a vector function, and we also have the keyword that's intersect, right, intersection, and you also have a surface equation right here. Okay, so to solve this type of problem is to parameterize the curve if necessary. But this time, we don't need that because it's already given to us. If you look at the problem right here, right? So the first step is already done for us. Okay, so that's just r of t equals to 2t t minus 1, 1, right? It's the same as the inside the problem. Okay, so now we're going to apply that mnemonic device is plug the curve into the, actually, never mind, it's not the plane, it's the surface, right? As we have discussed before. Plug the curve into the surface. Okay, so what I mean by that is, right, we have the equation of the curve, and we also have our equation of the surface. Right, it doesn't have to be on the first order, but I'm just using a plane as an example. So step 2, right, we have the surface is z squared equals to x squared plus y squared, right? So what we are going to do is we're going to do the same thing, right? Just like we did here. I'm gonna move this for convenience. All right, so I'm gonna separate this a little bit. So, right, this is our x of t, right? So this is our x of t. So we're gonna plug into here, and this is our y of t. So we're gonna plug into here, and this is our z of t, even though we don't really have a t. So that goes to here, right? So this will end up being 1 squared plus 2t squared plus t minus 1 squared. Okay. So we take that apart. 1 minus equals to 4t squared plus t squared minus 2t plus 1. And then we can cancel the 1, and then we end up with 0 equals to 5t squared minus 2t. And then what we get is t equal to 0, t equal to 2 or 5. Okay? So once we have step 2, what we're going to do is we have obtained the value of t, which it intersects. What we're going to do is we're going to plug in, right? We solve for t, and we can plug it back. We can plug it back into r of t, right? To find the intersection point, right? We can plug into the equation of the plane. We can also plug into the equation of the line, but I personally do prefer plugging in back to the curve because it's just a bit easier to obtain the answer. So for this problem, we're going to have p of t, p at the point, I'm just gonna pt, right? R equals to r of 2 over 5. That will give us 4 over 5, negative 3 over 5, and then 1, right? And the question is asking the x coordinate of the point where the curve is defined, right? So that means the correct answer is alpha, right? It's not, this is kind of a trick answer choice for the people who don't read the question very carefully, right? They just saw, oh, I saw for t equals to 2 over 5, I'm going to select answer choice Bravo, but that is not what the question is asking for. It's asking for the s coordinate, right? So let's go ahead and highlight these keywords for you to sort of better understand what the keywords are looking at. Okay, so let me go ahead and switch the orientation, right? Switch the orientation, not the switch notes, right? So this is the step-by-step process for you to solve the problem related to the intersection point between the curve and the surface, right? So we started with parameterizing the curve. We plug the curve into the surface. We solve for t, and then we plug in the t back into the curve equation, and then we can find the intersection point. Okay, so that's the idea. All right, let's go ahead and take a look at the second problem. So this is gonna be a fun one. Whoa, the answer choices are kind of wacky, right? I mean, again, I don't really mind. I mean, for this time, I'm gonna show you the answer, but maybe not next time. Oh, by the way, this is spring 2016. Spring 2016. I'm not sure if it's exam 1 or exam 2 or final. Oh, this is final. Okay, this is a spring 2016 final. And this one is spring 2020 exam 1. So the question is, find the vector function that intersects the curve intersection of the cylinder and the plane, right? And then, so this time is a little bit different, right? It's not a line and a surface. Right? So it's not longer a curve and a surface. It's a surface and a surface. And particularly, it's a cylinder versus a surface. In this particular case, it's a plane, right? So let me go ahead and return to these two documents, switch orientation, and I'm gonna move on to the next set of problems. Okay, so this is an type of problem. Is the intersection between a cylinder and a surface. Okay, so the keywords that we have here is we have the vector function curve. Never mind, it's not a vector function curve. It's just surfaces, right? Never mind. It's intersection between a surface and a cylinder, right? So I think I'm making some mistakes a little bit, but that's all right. And also you can see that the answer choices is the vector functions of parameterization and the bound, right? So if we look into the answer choices, we see the parameterization variable t. But the problem is, well, the parameterization is nowhere to be found, right? There's no t in here, right? So that tells us we need to parameterize, right? So we need to parameterize so that we can get an answer that's matching the answer choices. Okay, so enough of the rumbles. Let's go ahead and actually solve for it. So the first step is we need to parameterize the cylinder. With t. Okay, so how do you exactly parameterize the cylinder? Okay, so I am going to show you these examples. These sort of three standardized way of parameterizing it because of the right-hand rule that I mentioned in the 13.1 to 13.4 review of vectors. Because of the right-hand rule, if you want to draw a coordinate system like this, right? One is pointing up, one is pointing to the right. You have three options: is x, y, which everybody knows. You also have z, y, yz. Never mind, yz, and you also have zx, right? These are your three options that you can use. So to parameterize these in these three different scenarios, you can parameterize your variables in these fashions. So any of the horizontal variables, horizontal axes, should be written as a cosine of t, right? A cosine of t. And then any any variable that's on the vertical axis should be written with b sine of t. So as I said here, right, horizontal parameterize the variable on the horizontal or vertical axis with a cosine t or b sine t, as I just described here. So in this case, we are going to parameterize it's y squared plus z squared equals to 1. So that's going to be our second option, right? So we're going to have y equals to, so step 1, we're going to have y equals to cosine of t, because we have a unit circle with radius of 1. And then z equals to sine of t. Okay? Oh, that's step 1. And then step 2 is what I call is sub the cylinder into the surface, or instead of subbing the curve into the surface, now we are subbing the cylinder into the surface, right? So we have the surface of, right, so we have the surface is now parameterized as let me go ahead and, cylinder, right, is cosine of t squared plus sine of t equals to 1. So that's your y of t, right? So you have, you know what, I'm gonna write it in this way so I don't confuse with anybody, right? So that's your y of t squared, and that's your z of t squared, right? Okay. Let me just go ahead and expand it one more. Okay, just expand it one more. Y squared plus z squared equals to 1. And you substitute them, get this. All right, I hope I made this explained enough in detail for you. So I'm going to move it a little bit quicker. So step 2. Sub the cylinder into the surface. So we have the surface as x plus 2y plus z equals to 1. So that's your y of t, that's your z of t. So we're just going to plug them in. So what we're going to end up with is x equals to, don't worry, x plus 2 cosine t, right? Because y is corresponding to y of t, and then plus z of t, and that is just sine of t. So this kind of parameterization is, I think it's slightly different from the subbing, as I call it before, right? We're not plugging the actually, it's never mind. It's the same. The idea is very similar to each other. So now we're just gonna go ahead and rearrange the equation that we wrote it down above as x equals to something 1 minus 2 cosine of t minus sine of t. Okay, so what we after these two steps right now, what we end up with is y of t equals to cosine of t, z of t equals to sine of t, and we also have x of t equals to what we have just derived above, right? So now this is the curve that's the describing the intersection curve. Okay, so the step 3 is, right, solve for the remaining variable in terms of t, right? So we mentioned about 3 cases, right? And then we're just talking about the case 2. So we solved for the x of t right here. So I'm gonna label in pink as well. And then we're just gonna construct equation of the curve, right? R of t equals to, this. And then we can describe it in the parametric form, or we can also describe it in the vector form. R of t equals to this. Right, that's your x of t, and then you have your cosine of t and your sine of t. So that's your y, and that's your z. Okay, and there you go. I think we just have solved the problem. And then if you look at the answer choices that we have, I think we have answer choice B. Bravo. Okay, so let's review this one last time. So I'm gonna switch orientation. So for problems such as finding the intersection between a cylinder and a surface, these questions doesn't show up very often, but when it does, it's gonna trigger quite a few people because, oh no, I have never solved a question like this before, right? I only knew how to solve the intersection between a curve and a surface. Okay, now I just showed you how to do this. Right, first of all, we're going to appropriately parameterize the cylinder, right, with the parameterization variable t, right? And we have 3 different choices according to the right-hand rule. And then we're going to sub the cylinder into the surface. By what I mean is we're going to replace any variable in the surface equation with what we just parameterized above, right? The parameterized variable in the cylinder equation. Finally, in step 3, we're just going to solve for the variable in terms of t, right? So we're gonna step 3 right here, and then we have step 4 right here. Right, step 4 is just sort of wrapping it up, right? Construct the equation of the intersection curve. So that is all about 14.1 vector value functions. So I hope you enjoyed it. I hope you learned something, and I'll see you in the next video.